Good morning, dear students. Now I'm going to discuss about the application of molar conductance. There are mainly four applications for molar conductance. One is calculation of molar conductance at infinite dilution of weight, and second is determination of degree of dissociation of alpha of the weak electrolyte, and third is the determination of the solubility of sparingly soluble salt like AgCl, and fourth the conductometric titration. So we can discuss the each aspect separately. The first is the calculation of molar conductance at infinite dilution for weak electrolytes. As I already mentioned in the last class, that in the case of a weak electrolyte, it is not possible to determine its lambda 0 m, that is at infinite dilution, graphically, because its value going on increases with increase of dilution exponentially. So we need a method for the determination of lambda 0 m of weak electrolyte, that is using the Collatsch's law. Suppose we want to know the lambda 0 m of acetic acid, which is a weak electrolyte. It can be determined by the Collatsch's law. That is, lambda 0 m acetic acid is equal to acetate ion plus lambda 0 m of H plus ion. Okay. And this can be calculated by knowing the lambda 0 m value of three strong electrolytes like sodium acetate, HCl and NaCl respectively. Okay. By adding together the lambda 0 of sodium acetate and HCl and subtract the lambda 0 of NaCl from this sum, we get the lambda 0 of acetic acid as explained below. Yes. That is, lambda 0 of sodium acetate is equal to lambda 0 of acetate ion and lambda 0 of sodium ion, and lambda 0 of HCl is lambda 0 of H plus lambda 0 of Cl minus, and lambda 0 of NaCl is equal to lambda 0 of Na plus and lambda 0 of Cl minus. Adding the equation 1 and 2 and then subtracting equation 3, we get lambda 0 of acetic acid as shown below. That is this equation. And finally we get this, the result of lambda 0 of acetic acid. That is, again, lambda 0 of acetic acid is equal to lambda 0 sodium acetate plus lambda 0 of HCl minus lambda 0 of NaCl. Similarly, lambda 0 of ammonium hydroxide is equal to lambda 0 of ammonium chloride plus lambda 0 of NaOH minus lambda 0 of NaCl. Let's explain this in terms of a problem. You are provided with the lambda 0 value of three strong electrolytes, that is sodium acetate, HCl and NaCl. For sodium acetate, lambda 0 is 95.6, and for HCl it is 379.4, and for NaCl its value is 130.1. So we can use this data to calculate lambda 0 of acetic acid, that is CH3COOH. Okay, so you please do the data, use the data to do the problem. Okay, I hope that you have finished the problem, and those who are not familiar, I can explain this. That is, lambda 0 of CH3COH is equal to lambda 0 of CH3CONa plus lambda 0 of HCl minus lambda 0 of NaCl. There is 95.6 plus 379.4 minus 130.1, that is 344.9. Okay, the unit is Siemens centimeter square mole inverse. That is the unit generally used for lambda m. That is Siemens or ohm raised to minus 1 centimeter square mole inverse. So the second application, that is the determination of degree of dissociation of a weak electrolyte. As you already mentioned, the case of a strong electrolyte, its degree of dissociation is almost 1 because they are completely ionized. But the case of weak electrolytes, its degree of dissociation is not a constant, it changes with dilution. So it is interest for us to determine is alpha, the degree of dissociation at any particular concentration. As you know, the degree of dissociation of an electrolyte is defined as the fraction of the total amount of the electrolyte that have undergone dissociation, and it is expressed in terms of a decimal quantity or in terms of a percentage. For strong electrolyte, the value is almost 1 or 100%. For weak electrolyte, it is very much lesser than 1 or very much lesser than 100%. And alpha, the degree of dissociation, is equal to lambda Cm divided by lambda 0m. That means the degree of dissociation of a weak electrolyte is equal to the ratio of the molar conductance at a particular concentration to its molar conductance at 0 concentration. So that is very important. That is, by knowing this ratio, that is lambda C by lambda 0, it is possible for us to determine alpha, the degree of dissociation of a weak electrolyte. In this equation, C denotes a particular concentration and 0 denotes 0 concentration or infinite direction. So once again, the degree of dissociation can be determined by measuring two conductance value of the weak electrolyte. One is the conductance value at a given concentration and other is the conductance value at 0 concentration. Therefore, alpha is equal to lambda C divided by lambda 0. The next application, that application 3, that is the determination of solubility S of a sparingly soluble salt. You know that salt like HCl, PbCl2, barium sulfate, etc. are extremely small, soluble in water in very small amount, so they are called sparingly soluble salts. It is not possible for us to determine its solubility conventionally because it is extremely small, but it is possible for us to determine the even small solubility by conductometric measurement. The method is: prepare a saturated solution of AgCl by dissolving a known quantity of AgCl in a known quantity of conductivity water and warming it to about 60 degrees. Okay, that is, by warming a particular amount of proper amount of AgCl in conductivity water to about 60 degrees Celsius. Then second, the solution is cooled to room temperature, that is near 25 degrees Celsius, and measure the conductivity or the resulting solution using a conductivity cell of known cell constant. Then by measuring the conductance, it is possible to determine its specific conductivity Ksp, that is equal to conductance into cell constant. Once Ksp is known, we can determine lambda m. We can determine lambda m of the electrolyte by the equation lambda m is equal to Ksp into 1000 by m. That is lambda m is equal to Ksp into 1000 divided by m, where m is the molarity of the solution. Now I am applying a static assumption. Since the salt is sparingly soluble, it is assumed to be at infinite dilution. So we can make two approximations. Okay, one that is the lambda m can be taken as equal to the lambda 0 m. That is lambda m, the molar conductivity can be taken as equal to the molar conductivity at infinite dilution or zero concentration. And again, m, the molarity of the solution, can be taken as equal to S, the solubility of the salt in moles per liter. Therefore, the equation can be modified as lambda 0 m is equal to Ksp into 1000 by S. Therefore, S is equal to Ksp into 1000 divided by lambda 0 m of AgCl. As you know, the lambda 0 m of AgCl is equal to lambda 0 Ag plus lambda 0 Cl minus, that is known by the literature by the application of Collatz law, that is equal to 61.9 plus 76.3 respectively, comes to be 138.2 ohm raised to minus 1 centimeter square mole inverse. Okay, thus by knowing lambda 0 m of AgCl, we can determine the solubility S of the AgCl by using this equation. Once solubility is known, then the solubility product of AgCl Ks is the square of the solubility, that is equal to S square.